Here's an example of a one-tailed hypothesis test. We did one of these in class, but this is going back to that original packet that I gave you all, so we can work through the steps on a video where you can reference it. So in this one, we're trying to see if we think that a casino is cheating. Rolling 2 dice in a game and getting a sum of 7 would be considered to be good for the gambler. And so the suspicion here is that the dice are not fair, and so 7 is coming up too few times. And we can see here that they specify, support a claim that this dice sum to 7 fewer than 1/6 of the time. If dice were fair, they would come up a sum of 7 1 out of 6 times. So so the point here is that the thing we're wondering about is not just whether the proportion is 1/6 or not, but rather is the casino actually, do we think there's evidence that the casino is actually cheating by having dice that come up 1/6 too few times? And so that's a more specific claim. So we've worked through our steps. P is a proportion of dice rolls who sum to 7. It's a little weird when it's not people, but so P is a proportion of all the dice rolls that sum to 7 for all time. And of course, we can't roll the dice forever, so we have to base an inference about this on a sample that we take. And that's why we're going to only roll the dice 1,000 times for our sample. H0 is the statement. H0 is always the statement that that proportion is equal to something. And so 0.167, that's 1 out of 6. So if you do 1 divided by 6, that's what you'll get. And so that's the statement that the dice are fair. So that's the null hypothesis, is the statement that the dice are fair. If that were true, then we could do a standard error calculation using that value of P. And so this is that same formula divided by sample size. In this case, we intend to roll the dice 1,000 times. And that ends up being, let's see, so that's what I got on my calculator, 0.001 or 0.118. And that's enough information to allow us to label our p-hat distribution. And again, this is what the picture of p-hats would look like if the null hypothesis were true. So the center would be 0.167 because that's what the null hypothesis says. So that's where that center comes from. And then every tick mark is coming from the standard error. And so if I round this to 0.012, just to make my labeling easier, if I add 0.012, I'll get 0.179 for one tick mark. And then for the second tick mark, I'll get 0.191. Yes. And of course, subtracting, I'll have, subtract 0.012, so I'll have 0.155 and 0.143. So that's 2 tick marks in each direction. And again, that's assuming that's what the picture would look like if my H0 statement that's circled in green up there were true. The thing that makes this different from the other problems is that the HA here is not just that P is not equal to 0.167, but rather if we think the casino is cheating, then what we really believe is that we must have evidence that P is actually less than 0.167. And so that's our alternative hypothesis. Notice it still uses that 0.167. It's still an alternative to the null hypothesis. It's just a more specific alternative to the null hypothesis. The significance level is given in the problem, so that's 1%. It says it up at the last sentence in the problem says the significance level we're using is 1%, so that's 0.01. And again, that's what, that number is what small is going to mean for our conclusion. Remember, at the end, we're going to say something about a probability being small, and the definition of small needs to be decided in advance so that we're not biased by our data. Okay, so everything down through there has nothing to do with the actual data that was recorded. Only in step G do we finally compare this hypothetical universe that we've created to the actual data that we've collected. So p hat will be the actual data we collected. So 153 times out of 1,000, the dice really did sum to 6. And so that's 0.153. And we can compute a z-score for that. That's our observed value, which was 0.153, minus the mean. And I'm looking at my hypothetical bell curve up there, divided by the standard deviation. And I'll use all the decimal places that I possibly can from part C, just because I know I want to get z correct to 2 decimal places so I can use my table. So to 2 decimal places, this is negative 1.19, looks like. So it rounds to 2 decimal places like negative 1.19. We are always using 2 decimal places of that because of the nature of our table. So negative 1.19 is just here on the z-score. Notice this is the z-score distribution now. So a z value of negative 1.19 would be right there. That makes sense because the p hat value that we got, this p hat value, if I drew it up here, it would have been right about there. 0.153 is just to the left of 0.155. And you can see how relatively that's the same as it is in the bottom picture. The whole reason we draw the bottom picture is because that's how our table is organized. So we know that we want to shade the tail of this, but because our alternative hypothesis has a less than sign, then we're only shading to the left. This is what we would call, we were talking about p-value before, we called this a one-tailed p-value. And so this is called a one-tailed hypothesis test. If you remember in class, I was saying the difference is if we go back to the original distribution problems like the one we had for women's heights, if you had, I think we had a 57-inch tall woman that we were interested in deciding how unusual that height was, where the mean was 65. And we said we could figure that out by converting to a z-score and looking at our table. But there are 2 different ways to think about that unusual value. You could say, what's the probability that I get someone who is that far from the mean, in which case you mean that far from the mean either because they're very short or because they're very tall. You're interested in just how unusual they are in terms of their distance from the mean. That would be the case where we'd be using a 2-tailed p-value. But if we said a 57-inch tall woman is unusually small, and we said, well, what's the probability of someone being that small, then you could justify only paying attention to values to the left. In other words, you're unusual because you were that small or smaller, rather than just that you were unusual because you were that far away from the mean. So it makes sense that the 2 different things come up in different situations. And the only practical difference is that we have to pay attention to our HA statement because it will indicate to us which one we're doing. And then when we go look up our values in our table, we have to remember that we're not trying to find the area on both sides, so we're not doubling anything. Anyway, so in this case, the table tells us exactly the area that I've drawn there. If I look up negative 1.19 in the table, the area that we read off of the table will be exactly what we see shaded there. And so if I do that, my 4 decimal places for that would be 0.1176. So that's how much area is shaded in that picture. And that would be my p-value. So we're trying to make a conclusion in our significance test, which means, I just have to decide if that p-value is small. That seems like a rare probability, but notice it's almost 12%. So generally we wouldn't consider something that size to be small, but we don't have to decide it on the fly. We go back to our step F and realize that the alpha that was specified there is what small means for this problem. And so in this case, the p-value is not small because 0.1176 is not smaller than 0.01. So we do not reject H0. In other words, we're saying that the picture that I drew, so the picture that I drew up here, is consistent with the data. We're not saying that we've proven that the picture is true. We'll never say that. So we'll never write that we accept H0. What we're saying is that the picture and the data are consistent. That's what it means to say we do not reject H0. And so when we're trying to say this in plain language, we don't want to say p-values and H0s and all kinds of stuff that's all statistical. We want to look at the original problem, which was just, are the dice loaded? That was the original question. So we say here, we do not have enough evidence or significant enough evidence to conclude. And then what I'm writing in the space here is always statement HA. And so in this case, the HA was that the probability the dice come up 7 is lower than it's supposed to be. In other words, that the casino is cheating. So I could just say, as my HA, that the dice are loaded. So this experiment does not prove that the dice are loaded. So it would not be enough evidence to accuse the casino of any wrongdoing.